Bismillahirrahmanirrahim. Assalamu alaikum viewers, welcome to my channel, and in today's video we are going to discuss the examples of the orthogonal trajectories with respect to the polar coordinates. And as far as the derivation and theories was concerned, we discussed it quite exhaustively in the previous video. That's said to be the first part of this video series. You can see the link in the description box for more deep insight. Okay, so right after that video I recommend you to move on to this one, not before that. Okay, so now in the previous video, as we discussed, that if we are having a family of polar curves, and what is going to be the slope of that curve, the slope of that curve at any subjective point is actually the slope of the tangent that we are going to draw over there. So the slope of the tangent or at a subjective point was discussed to be like this. Okay, and we just called it tan phi. Okay, so if we are having a certain slope of a tangent line at a particular polar curve at a certain point, and what is going to be the equation of the orthogonal trajectory, we discussed there that, for instance, if we are having, like, this is said to be a radial axis, and we just call it r, and we just draw there a curve over here like this. Okay, and this was said to be angle theta. We are having a certain family of curve out of which I have just picked up one curve, okay, a single curve out of that family. And at a certain point, if I just say at this point, which is represented by the coordinates r theta, okay, I just draw here a tangent. Okay, the slope of this tangent, I just say that it is said to be tan phi. Okay, and it was driven to be having this value. All right, now similarly at the same point r theta, if we are having another curve, there's another curve that is being intersected at this point, the tangent that we are going to draw over there should be exactly perpendicular to this tangent. Okay, exactly perpendicular, and this tangent is representing a curve that should be either like this or like this. It's simply a revision that I'm just doing right now. Okay, and the slope of this tangent line I just represent as tan phi 1. All right, and these two tangents are exactly perpendicular to each other, you can see. So you can see that this curve is orthogonal trajectory of this curve. All right, so that's what we are going to refer in the examples. Okay, so if I just say that tangent phi is having this formula, then the tangent, the slope of the tangent of the orthogonal trajectory of the given family of curve is going to be the negative reciprocal of our tangent phi. Okay, we are going to take the help of this concept. All right, now let's move on and see the example here. I just say that I'm having a question, r raised to the power n is equals to a raised to the power n cosine n times theta. Okay, this is a question, and it is representing a family of polar curve once when you just substitute the value of n moving from 1 to so on, all the natural numbers you keep on substituting, you're going to have family of curve. We are going to discuss it graphically right after solving this question. Okay, so we are asked to find out the equation of the orthogonal trajectory of this family of curve. Okay, so orthogonal trajectories equation is also going to be representing another family of curve which is going to be exactly perpendicular, or whose tangents at the point of intersections are going to be exactly perpendicular to the tangent of this family of curve. Okay, so what we have to do, I just represent this equation as equation number 1, and now I'm going to differentiate both sides with respect to my r. Okay, so with respect to r begin. All right, so an something constant, so we just write it before the operator. It's like this. And just apply the basic derivative formulas and do it as rapidly as we can. And over here we are going to apply a chain rule. It's like this. So it's going to give me n is going to be written outside because it is a constant value. So I'm going to have a stuff that looks something like this. Worst bike riders without silencers. Okay, so now this n and this n I just cancelled out. Rn minus 1 is equals to negative En d theta by dr. Okay, now I'm going to shift this term over here. Okay, so and theta. Now I say that I should have r along with d theta by dr, so I'm going to multiply both sides by my r. Okay, so it is therefore gonna be alright, so this thing is equal to this. Now you see here at the place of Rn, how about if I just substitute this value? Okay, the Rn is equal to this, so I'm going to substitute this thing at this place just to simplify my expression. Okay, this will help us in getting the orthogonal trajectory equation in less in a span of time, small span of time, like that. So okay, so it'll be therefore r d theta by dr equals to negative. So Rn was actually an cosine of n theta upon an sine of n theta. An and this thing gets cancelled. All right. So what is left now is, so this is the general formula of the slope of all the tangents that we are going to obtain at the intersection points of which family of curve? This family of curve. Okay, this is the general formula. So now we are going to find out the general formula of the slopes of the tangents of the orthogonal trajectory. So the general formula of the slopes of the tangents of the orthogonal trajectory will be the reciprocal of this value. Okay, so the general formula of the slopes of the tangents of orthogonal trajectories at particular points of intersections, of course, points of contacts or points of intersections, is going to be negative reciprocal of this thing, so it'll be inverted, and this negative sign will definitely going to be cancelled. So it'll be this, so it is going to be written like this. Okay. Now we are going to apply the method of separating variables. So we are going to swap this term over here and r and dr on the other side. So it will be therefore 1 upon r dr, and this will be cos of n theta upon sine of n theta dt. Okay, now we will integrate both sides in order to get the solution of this differential equations. I hate bike riders. Okay, this is it. Now this is quite easy to handle. I mean, we can easily integrate just directly applying the formula. Over here we have to apply the substitution process. I can do it directly, but it's my habit to be quite exhaustive in my work. So I'm going to apply a substitution process. So I will do what? I will just assume that let n theta is equals to t, and this, if I just differentiate both sides with respect to the original variable theta, then I'm going to have this thing. So d theta is equals to just like this. Okay. So this is gonna provide me a picture like this. It's gonna be cosine of t upon sine of t. Okay, dt equals to ln of r plus some constant. I'm going to represent this constant as my ln of c, like that, and that's it. Okay, now again I'm going to apply a substitution process. So here I just say that let sine t is equals to u, the differentiating both sides with respect to the former variable, which is t. So once when I differentiate both sides with respect to my t, it's going to give me cosine of t is equals to du by dt. So this thing tells me that cosine of t dt is equals to du. Alright, so that's how the thing happens. Okay. Now over here I can apply the formula, I can use the characteristic of my logarithm, the primary or the intrinsic characteristic that you say. So the addition of two different logs is actually the log of product of these two values. So you can write it like this. Alright. Okay, so over here now just directly apply the formula of 1 upon u integral. It is ln of u, and there you go, ln of u. Okay, just like this. Now over here again apply the primary characteristic of your logarithm, that if you're having log of some value having power in it, it can be written like this. Okay, so that's what we are going to apply here. We are going to restore our formula. It is going to be written something like this. Now as we are having logarithm at both sides, we can cancel it directly, or we can apply exponential. It is going to cancel out the effect of the logarithm. It's like that. You can cancel it directly because you're standing at the advanced level. So that's how it looks like. Now we just restore. The value of u was actually your sine t. Is equals to rc. And t was your n theta. Your n theta. Now I don't like this 1 by n power, so I'm going to remove it. How I'm going to remove it? I will apply power n at both sides. So it's over here. So applying power n at both sides, applying power n at both sides. Okay, so c power n. Now I can shift this c power n over here, and as this c was a constant number, so you just apply any power of n on it, it's going to give you a constant number. If we take the reciprocal of that constant number, again you're having another constant number. So this is entirely a constant thing, you see. So you can represent this constant thing by another constant value. Okay, so you can represent it like this. You can represent it like this. Okay, like 1 upon c power n. I can represent it with another constant value, just to beautify my values, and that's it. It's like that. So now this is said to be the solution of this differential equation. Okay, and this solution is representing the function of the family of curve of the orthogonal trajectories of this family of curve. Okay, but that's it. Now, as we have obtained that the orthogonal trajectory equation of the orthogonal trajectory, or the function representing family of curve of the orthogonal trajectories of this family of curve, is having this equation. Okay, so both these family of curves are orthogonal to each other, means the points where all these curves are going to intersect each other, at those points, when you just draw the tangents, they are going to be perpendicular. Okay, now we are going to verify this thing graphically. Let's move on.